everyone. My name is Bowen, and I'm a chemistry PhD student advised by Yuri Lisipik and Vijay Pandey. And so today it's my pleasure to talk a bit about our recent work on machine learning for small molecule lead optimization. So I'm sure a lot of us here have probably seen this graph. And this graph essentially shows the number of drugs that is developed per $1 billion of R&D spend. And we see that over the past 50 years, this cost efficiency has been decreasing exponentially. So there's a lot of reasons for this, but regardless, this kind of motivates us to see if there are tools that we can develop to kind of make this process more efficient. So in particular, we focus on the lead optimization process, where starting from a hit molecule, you're kind of through a series of designing, making, and testing molecules, you're trying to eventually develop it into a drug candidate. And our thesis is that machine learning can be used to speed up and improve this process. And so in particular, so this talk, I'm going to focus on two of our recent works, one on molecule property prediction and another one on molecule generation. So this is one of our very recent works on molecule property prediction. And the task here is essentially, given a molecule, can you predict one of its properties, right? Whether it's toxic or not, whether it binds to a particular enzyme or not. And the motivation here is that actually experimentally testing molecules can be pretty expensive and time-consuming. So if we could build a model that can make these predictions and we can run like virtual experiments, then it could hopefully speed up the process. So there are challenges in this problem. One of them is that we just don't have a lot of label data. And because what I mentioned before, you need expensive experiments to get these labels. So as a result, a lot of these machine learning and deep learning models tend to overfit to these very small training sets. The other issue is more of how we use these models, right? We want to use these models for scientific discovery, right? We want to make predictions on examples that we may have never seen before. And so by definition, there's usually a mismatch, right, between the examples you see during test time and the examples that your models that were trained on. And empirically, we see that a lot of these models tend to perform very poorly in these prospective settings. So it seems transfer learning could be a natural solution to this, right? Because there's a lot of data, a lot of unlabeled data, and also a lot of labeled data, but for other kinds of properties, maybe not for the ones that you're interested in. But the issue here is that we've seen empirically that just naively applying transfer learning approaches, such as multitask learning or pre-training, can, and a lot of times, lead to worse results, right? We call this negative transfer, and there could be a variety of reasons for this. And the issue is, a priori, it's hard to tell whether pre-training or transfer learning could help or hurt your performance. So this work, we do a systematic exploration of of different kinds of pre-training strategies, in particular with graph neural networks that Yuri talked about yesterday in a graph classification setting. And the conclusion for this work is that we need to combine both a node and a graph level pre-training technique to reduce negative transfer and improve generalization performance. So I know Yuri talked about this yesterday, but I'm going to briefly go over graph neural networks for graph classification. So these are neural network models that operate on graph structured data. And for graph prediction, they operate in two steps, right? So the first step is you perform a message passing step where for each node receives information from its neighbors and then updates its own state. And after a few series of this message passing, you obtain updated node embeddings that kind of summarize the local neighborhood. And then you kind of pull together these node embeddings to obtain your final representation that summarizes your overall graph structure. And I guess our insight is that if you trace how the neural network makes these predictions, then it kind of depends on having good node embeddings, right? That are able to capture the local structure similarity and are able to be pulled together to form graph representations that summarize the graph well. And also because we operate on real objects, molecules, and they're not just abstract graph objects, we also want to capture some kind of domain information. So this kind of cartoon shows our hypothesis for how to improve pre-training. So we kind of differentiate between a graph level and a node level pre-training. And this kind of refers to where we provide the training signal. So a node level pre-training uses the node embeddings to make a prediction, and whereas a graph level pre-training technique uses the final aggregated representation to make a prediction. And our hypothesis is that if you look at the center slide, if you just naively apply a graph level pre-training approach, for the molecule case, it would be maybe pre-training on publicly available data sets with auxiliary labels, then of course your graph embeddings themselves are expected to be well separated, but there's no guarantee that your constituent node embeddings are well embedded, right? And our hypothesis is that only by combining both a node level and a graph level pre-training approach can we both have well-embedded nodes and well-embedded graphs, which allows you to transfer to a wide variety of different downstream tasks. And so we come up with a few different node level pre-training techniques. I'm just going to go over one of them, and we'll call this context prediction. So we apply the distributional hypothesis to the graph domain. And the idea here is that given a embedding of a particular subgraph, we want to predict what its surrounding context is. And this is kind of the donut that surrounds the central subgraph. And the idea here is that if the model can do this task well, then it's able to learn to embed nodes that capture the local structure well. And this kind of follows from chemical intuition. And so we test this on a molecular property prediction. And in particular, we look at it as a binary classification task. So given a molecule, predict a yes/no for whether it's active for a particular property. And then we test this on 8 downstream data sets from the molecule net benchmark. We also apply a special kind of scaffold split to test for generalization ability to ensure that the molecules in the test splits are very structurally different from the training splits. And so we show that doing this approach kind of improves generalization performance, right? You see the green bar on the right is when you combine a node-level context prediction with graph-level supervised pre-training. And this is the improvement in rock AUC on average over no pre-training. So this results in a 7% improvement over no pre-training, and also a 4% improvement with just the orange bar of just doing naive graph-level pre-training. And if we look at the individual performance on the 8 different downstream data sets, we see that the orange dot is if you just naively apply graph-level pre-training, and we see that there's 2 data sets in which we kind of see some negative transfer. But if you combine both the node-level context prediction with the graph-level supervised pre-training, then you eliminate the negative transfer in these 2 examples. And so the conclusion here is that if you want to pre-train graph neural networks for molecule property prediction, then you should combine both a node-level and a graph-level pre-training approach to both reduce negative transfer and improve generalization performance. So the next work I want to talk about is our work from last year on molecule generation. And the kind of task here is we want to generate molecules that are both valid, realistic, and have desired properties. And the motivation here is that there's just so many molecules out there, right? We've made probably 10 to the 8 molecules in history, but it's been estimated that maybe there's up to 10 to the 23 to 10 to the 60 molecules that are possible, which are drug-like, right? So chances are any future drugs or future materials are going to be stuff that we haven't seen yet. And so there has been some recent work, actually there has been a lot of work on molecule generation. A lot of research has been done on using a text generation approach, where you kind of represent a molecule as a special text sequence, and then you use kind of text generation models to generate these sequences. The issue here is that actually a text sequence is pretty fragile, right? Small character changes can result in a big change in the molecule structure, and actually small changes can completely invalidate what the structure is. There's also more recent work on using graph generation approaches where you directly generate a graph. And there's also a lot of challenges in doing this well. But our work kind of focused on the graph generation approach. So we basically want a model that can generate graphs that fulfill kind of 3 objectives, right? We want it to generate graphs that can optimize for a particular objective, for example, drug likeness or potency. We want these graphs to obey underlying rules, right? Like, for example, obey chemical laws. And also, on top of being valid, we also want these graphs to be kind of realistic as well. And so we developed this model called the Graph Convolutional Policy Network that combines kind of three ingredients. We use a graph representation, so we directly generate graphs. We use reinforcement learning to directly optimize for the particular property that we're interested in. And then to ensure that the stuff we generate is realistic, we use adversarial training. So we provide the model with a set of examples that we say are realistic, and we're asking the model to kind of generate stuff that are similar to this. And so we treat, this model treats the graph generation process as a kind of Markov decision process where we generate the graph step by step. So just quickly, a quick overview. So we start off with our kind of partially completed molecule, right? And then we insert dummy nodes that tell us what the possible atoms are. Then we use our graph neural network to compute the next state, which consists of basically the updated node embeddings. And then from these node embeddings, we sample the next action, which consists of two atoms and the bond type that we should create between the two atoms, right? And then if this action is actually valid, right, then we perform this action and we give it a small positive intermediate step reward, right? And we keep doing this until we sample a stop action, and then our graph is finished. And then we calculate the molecule property of our finished molecule graph, and then that's our final reward. And so we train this in this kind of procedure. So we have the molecule generator in red, and we iteratively generate our molecule graph, and then we compute our rewards from that. We also have a green, this discriminated in green, that compares how similar our generated molecule is to the set of realistic molecules that we provide, and then provides this kind of adversarial score. And then we combine these two scores and use reinforcement learning, in this case a policy gradient approach, to update our red generator such that it's more likely to generate molecule graphs that are valid and have high properties. And so we test this model on three tasks. Property optimization, where we just want to optimize the score of a molecule, of generated molecules. We also do property targeting, where we want to generate molecules that have properties that kind of fall within a specified range. And then also constrained property optimization, where given a starting molecule, we want to kind of edit it to increase one of its scores. And so, yeah, we use a set of commercially available molecules as our kind of realistic data set, and then we compare our work with two baselines. Basically, for the property optimization experiment, we show that our GCPN model can result in like 60% higher property scores, and we tested on log P and also QED, which is a measure of drug likeness. So here are some of the generated molecules. And for the property targeting results, so we have log P and molecular weight, and we have two kind of ranges that we want to generate molecules for. And we show that our model has up to 7 times higher success rate than one of the baselines. And also on the constrained property optimization, where given a starting molecule, we want to edit it to get a higher score for log P. We show that for a range of different similarity constraints, so like how similar the final edited molecule is to the starting molecule, we have up to 180% improvement in the score. And so here are some examples. So starting structures, and we make some edits to get a final structure with an increase in the score. So in conclusion, this work showed that you can actually generate pretty complex graphs in a kind of sequential generation process, and that the model that we created, the GCPN model, can generate molecule graphs that are valid, realistic, and also have desired properties. So to conclude, I've said lead optimization is a pretty important part of the drug discovery process, and I've showed 2 examples in which we use machine learning to hopefully speed up and improve parts of this process. So thank you.